The rocket was destroyed 293 seconds after launch. Not because the engines failed. Not because the fuel system ruptured. Not because the spacecraft was built incorrectly. America's first mission to another planet died because one tiny handwritten mark never made it into the code controlling the rocket. And 4 minutes after leaving Earth, one of the most advanced machines ever built began steering itself toward disaster. On July 22, 1962, the United States was about to attempt something it had never done before: send a spacecraft to another planet. The mission was called Mariner 1 Launch Failure. Its destination was Venus. The rocket carrying it was an Atlas-Agena booster. Standing at Cape Canaveral, engineers believed they had done everything right. The engines ignited. The vehicle lifted cleanly. Telemetry streamed back exactly as expected. And then the line and the guidance display began bending sideways. Fast. At first, nobody panicked. Small trajectory corrections were normal. Rockets drifted slightly during ascent all the time. The onboard guidance computer was designed specifically to correct those deviations. That was the entire point. This was the new era of automated spaceflight. Computers would react faster than humans ever could. The system was trusted. Completely. But inside Mission Control, engineers were about to learn that the rocket was not correcting its path. It was amplifying the error. And every second, the correction system was making the trajectory worse. The guidance computer aboard the Atlas-Agena had one job: track the rocket's flight path. Compare that path against the planned trajectory. Make constant steering adjustments. Simple in principle. Except this system depended on something invisible. A mathematical formula, handwritten long before launch. That formula was part of the ground guidance equations controlling how the rocket interpreted changing flight data. The rocket itself was receiving information through radio guidance from Earth. But raw data during launch is noisy. Atmospheric turbulence. Minor vibrations. Temporary signal instability. So engineers had built something critical into the equations: a smoothing function. It filtered out meaningless fluctuations. The rocket would ignore random disturbances and stay on course. That filtering process depended on one tiny symbol: a handwritten overbar. One small mark above a variable. It looked insignificant. It was not. Somewhere during transcription, that symbol disappeared. No one noticed. And suddenly the system lost the ability to distinguish random noise from real flight movement. The computer was now trusting bad data, but nobody knew it yet. For the first several moments after launch, everything still looked normal. The engines were stable. Acceleration was nominal. The booster climbed exactly as planned. This is what makes hidden dependencies dangerous. The system looked perfect because the fragile piece supporting everything had already failed silently. Then the rocket encountered minor atmospheric disturbances. Normally, the guidance system would smooth them out. Instead, the computer interpreted every tiny vibration as a legitimate course deviation and immediately began steering against them. The corrections started small. Tiny gimbal movements. Small engine vector changes. Nothing dramatic. Until those corrections created new movement, and the computer interpreted that movement as another error. So it corrected again. And again. Each correction created more instability. The machine had entered a feedback loop. It was now fighting itself. And that telemetry line inside mission control started bending harder, faster, more violently. At first, engineers assumed the rocket might recover. Automated systems were supposed to stabilize situations like this. That was the promise of modern guidance computers. Remove human reaction delay. Allow machines to control precision flight. But now the rocket was drifting westward over the Atlantic. And this changed everything. Because this was no longer about losing a spacecraft. This was now a public safety emergency. The Atlas booster was enormous. More than 90 feet tall, loaded with propellant, traveling at tremendous speed. And directly below its unpredictable flight path sat commercial shipping lanes. If the rocket broke apart over civilian vessels, the consequences could be catastrophic. Inside the launch control room, engineers stared at the same screen. The same telemetry line. But its meaning had changed completely. Minutes earlier, it represented success. Now it represented danger. The trajectory curve bent farther away from its planned path. The correction system kept firing. The rocket began oscillating. Large side-to-side steering movements started appearing. The machine was no longer navigating toward Venus. It was inventing its own path. And nobody had enough time to understand why. This was 1962. Computers were still new. Software engineering barely existed as a discipline. There were no modern debugging systems, no simulation environments, no automated error validation. Millions of dollars in hardware were now being controlled by equations manually copied by human hands. And that tiny missing symbol had become more powerful than the entire spacecraft. Then came the final decision. The range safety officer watched the telemetry line continue bending off course. The rocket had crossed safe flight boundaries. There was no recovery. There was no time left. At 293 seconds after launch, he pressed the destruct button. Instantly, the Atlas-Agena exploded over the Atlantic Ocean. America's first interplanetary mission was gone. Years of engineering vanished in a fireball. The spacecraft never reached space. But the explosion itself was not the worst consequence. The real damage came afterward. Because suddenly, one terrifying question appeared inside the entire American space program. Could computerized flight systems actually be trusted? Until Mariner 1, Automation represented the future. Machines were supposed to remove human error. Precision mathematics would outperform manual control forever. But this disaster exposed something engineers had underestimated. The machine itself had worked perfectly. Nothing mechanical failed. No hardware broke. No engine malfunctioned. No fuel tank ruptured. The computer followed its instructions exactly. That was the problem. Its entire decision-making process depended on one microscopic human action performed weeks before launch. One handwritten symbol. One invisible omission buried deep inside documentation. And the machine obeyed that mistake with absolute precision. That lesson permanently changed aerospace engineering. NASA began restructuring software verification systems. Independent equation checks became mandatory. Documentation procedures became stricter. Engineers stopped assuming advanced machines were inherently reliable. Because reliability was not determined by complexity. It depended on every invisible layer underneath. And the image everyone remembered was not the explosion. It was that telemetry line. At first, it showed a rocket heading toward another planet. Then it bent sideways. Then engineers realized the machine controlling the mission was not broken. It was doing exactly what it had been told. The rocket did not fail in flight. It failed on paper. One missing mark was enough.